Hello, today we're going to be watching video 3, and video 3 is all about graphing and density. So we're kind of tackling two topics that will come up a lot this year. Density being our current topic and graphing kind of being our ongoing topic. So anytime you hear me talk about graphing, you'll often hear me refer to tails and dry mix. Let's talk about what those two things are. First, let's focus on the tails. Tails stands for title, axis, interval, label, scale, and summary. So, when we say title, we're looking for a title that relates both the independent variable and a dependent variable. So if we're doing a experiment on the effect of sunlight on plant growth, we can't call it hot stuff or sunny side up or anything jazzy like that. We want to title it actually something that relates the independent variable to the dependent variable. So the effect of sunlight on plant growth, or sunlight and plant growth, hours of sunlight and plant growth. We would definitely want to relate those two. Axes. Axes is the plural of axis. So when we're talking about the y-axis and the x-axis, plural is axes, so that's where that comes from. And that has to do with putting the right thing on which axis, which is where dry mix comes in. It turns out that the dependent, also known as the responding variable, will always go on the x-axis, and the manipulated, or the independent variable, will always go on the x-axis. The one exception to this tends to be time. That typically won't happen in our class. We'll see that a lot more in physics. Interval. Interval means that the spaces in your graph, the boxes on the graph, are of equal spacing, so that if you're counting by twos, going left to right, that you continue to count by twos or tens or five, that interval is consistent. Same thing on the y-axis. We want those intervals, those boxes, to be consistent. Label. Label means to label your axes, including units. Scale means that you're taking up a good size of the page so that you can actually see things accurately, that you're not making a graph that's only 2 inches big and then you can't make any extrapolations, which means to guess forward beyond your data. And then last but certainly not least is a summary. You're expected to write a 2-sentence summary about anything that you graph. That is actually a part of your graph. So again, always remember your tails, and when it comes to the axes, remember your dry mix. Okay, now let's talk about density. So we all know that the equation to a line is typically y equals mx plus b. That's our standard algebraic equation for a line. Now let's say that we graph the mass of a substance after we manipulate the volume. So we keep adding liquid to a graduated cylinder, and we keep weighing the graduated cylinder, and we figure out what the mass of the liquid is. So we're adding more and more liquid, and we're coming up with new masses. We're measuring new masses. Okay, so that's our scenario. If that is the case, then when there is nothing in the container, we have no mass and we have no volume. And so this b, which is our y-intercept, will actually disappear, and our equation becomes simplified, and we wind up with y equals mx. All right, that's pretty good. Now, if we were to graph it in such a way that our y is our mass, and our m is still our slope, our x, what goes on the x-axis, is our volume, because remember, we manipulated the volume and then we measured the mass, then we wind up with kind of an interesting equation. What is that m? Well, it turns out that slope, if we try to solve for the slope, we wind up with mass over volume, which means that the slope of any line where you're graphing mass on the y-axis and volume on the x-axis, density will be your slope. So let's look at some examples of that. Here's our first graph, and I'm going to kind of pull this a little bit forward into the light because I wrote it in pencil, as you would do. So you can kind of see that at the top of our graph, we have some data here. Actually, this is graph 2. Let's go back to graph 1 first, make it a little bit simpler. So In graph 1, we start out with these various measurements of volume. We're adding liquid, and we're measuring the mass each time. If we were to graph these numbers, we would wind up with a graph that looks like this. Notice that I have a title that relates the independent variable to the dependent variable. I have my mass, which is my dependent variable on the y-axis. My x-axis is volume, or my independent variable. My interval is consistent on the x-axis and the y-axis. That doesn't mean, in this case, 2 boxes is 10, and in this case, 2 boxes is 50, but the important thing is that I'm the same on both sides. Scale, this is a pretty decent sized graph. And I have a summary. If I look at my graph, as volume increases, mass also increases. We're not looking for anything super long. We want it quick and concise, but so that you can see it. So it turns out that if I measure the slope of this line, I actually would have the density. Density is mass over volume, so I would, at this point, I have 50 over 10. So at this point, my density is 5. If I were to measure each of these points, or just the slope of the line by taking 2 points, a change in y over change in x, I would actually have my density. Now let's look at a different scenario. So here's a scenario where we have 3 different substances, and for each of them we changed the volume and we measured the mass. So all of these are actually masses of these substances. Let's write that in. Mass in grams. All right. Now if I were to graph each of these on separate lines, I would have a graph that looks like this. And it turns out that A has the lowest slope, followed by C, followed by B. Well, if density is the same as slope, the one with the steepest slope, B, would be the most dense, and the one with the least steepest slope, A, would be the most dense. Notice that my graph here has a title that relates the independent variable and the dependent variable. It also has the proper axes. The intervals are consistent. And from there, I have a good size. I have labeled my axes. And I have a good summary. So all of my tails and my dry mix has been adhered to. Over the course of the next couple weeks, you'll see that we'll do a couple labs. Make sure you keep these things in mind when you're graphing. Come back to this video and see if you can help yourself to figure out what data you have formed. Your graph may not always have a perfect straight line because you're using experimental data, and experimental data sometimes has errors. But if you learn to become a little bit more accurate, those things will slowly disappear with time, and you'll get nicer and nicer graphs. Thanks so much. Bye-bye.